This is my attempt to try to understand the literature of integrable models, both integrable lattice models and more recently integrable field series, from some viewpoint of gauge theory, which is 4 dimensions. So I call this the 4-dimensional Chern-Simons theory, which is a little bit the non-standard name, because we learned that in textbook that Chern-Simons theory doesn't exist in 4 dimensions. But I'm going to explain what I mean by this theory. And integrable models are a very rich subject and has a variety of different aspects. And I think it's impossible to try to understand everything from a single framework. But nevertheless, at least this viewpoint clarifies a lot about, first of all, why integral models exist. And not only that, try to see the pattern of the existing integral models and also do some computation. So that's what I'm going to explain in this talk. And this work is based on collaboration with Kevin Costello. So I hope you can see the second, you see the second slide. And this work is in collaboration with Kevin Costello, who is at the Perimeter Institute, and Ed Witten, who is at the Institute for Advanced Study. And this is an interesting collaboration in the sense that some of the question itself has been around ever since Ed Witten worked on Chern-Simons theory long ago. And naturally, he was working on Chern-Simons theory very famously. And he was trying to use the Chern-Simons theory to try to understand the integrable models. But unfortunately, he didn't quite succeed. He succeeded in some aspects, but definitely not in understanding integral model in itself. And that was the early 90s or so. And since then, a lot of people worked on various aspects of Chern-Simons theory, but this particular question has been kind of forgotten. And the situation changed only quite recently in 2013 when Kevin Costello wrote a paper, which is more or less like a mathematics paper, but nevertheless contains also a lot of interesting physics inside too. And that paper itself contains many mathematical gadgets, which was hard for me to understand. So we tried to understand his paper and try to understand everything in a more physics friendly language. And that's what we tried to do in this project. And along the way, I think we clarified a lot of interesting aspects of the story. And so far, we have written 2 papers on the subject. Well, part 1, which appeared in September last year, and part 2, which we put in the archive in February. Oh, sorry. So this is in collaboration with Kevin and Ed, and we are now writing parts 3 and 4 with Kevin and myself, and we are writing the paper, and hopefully they will appear soon. So the reason that there are many papers is that, well, first of all, we need to cover a lot of material. In fact, if you sum up the pages, it's more than 300 pages or so. So it's a lot of material. But partly, we want to discuss different aspects of the story. So in integrable models, there are people actually mean different things. For example, people talk about integrable lattice models. That's the first thing. That's the thing discussed in the first 2 papers. So namely, for example, like Ising model and things like that. So those are the integrable lattice models defined on the discrete lattice. And we try to understand those in the first 2 papers. And in the forthcoming paper, we try to understand integrable field series, like ON model and things like that. And we discussed both classical and quantum aspects of the story. So classical integrability, which may or may not lead to quantum integrability, and why and when they lift, that's the type of the question. And so this is a lot of material, and there are certainly a lot of details, but today I try to make the talk hopefully accessible to many of you, and also try to explain the material in such a way that the connections between different parts of these 4 papers are somewhat manifest. So I try to explain, for example, part 3 of the paper by motivating from part 1 of the paper, etc. So I try to emphasize the interconnections between them. Well, in fact, to some extent, subtly a little bit more than is necessary, but many of the stories stand on its own. But today, at least, I like to explain the story in such a way that the interconnections are clear. Okay, so let me first come to first do this part 1 and 2. So that's about the integrable lattice models. And since this is a conference on integral models, I'm sure many of you are very familiar with integral models. But nevertheless, just to clarify what I want to study, let me come to the very famous Yang-Baxter equation. And I want to, so first of all, for integrable lattice models, well, because I'm saying this because there are various different definitions of integral models. And it's a little bit dangerous if we just talk about something and then other people think that think of integrability in another definition. So let me make clear first in the first part of this talk, by integral models, I just mean the solution to the Yang-Baxter equation. So Yang-Baxter equation is this represented graphically, of course, this equation. I'm sure that all of you know this. And then it just means that it's a factorized scattering. So it's a product of R matrices. And the product in different orders give the same answer. So this is a celebrated Yang-Baxter equation. Except that today, well, I define the integrable lattice models as a solutions to Yang-Baxter equation with the spectral parameters. And so for each of these lines, I might call these rapidity lines. So there are 3 lines here. And for each of these lines, there's some parameter, which I load as Z1, Z2, Z3 for each of the 3 lines. And R matrix depends on these spectral parameters. So when 2 lines cross, the R matrix depends on these 2 spectral parameters. And these spectral parameters in general takes values in some curve, which for most purposes is a abelian manifold, like a complex number or torus, etc. So you can define the sum and then the difference, and then here I use the notation minus. So anyway, so that's there. You can tentatively think of these as complex parameters simply, and R matrix is a difference of spectral parameter.
Sorry,
and then of course,
can I ask a question? I mean,
oh, yeah, of course, yes.
So this is a particular class of integrable lattice models. So it's fundamental
Yes.
spin model where R matrix is difference variable and what we call L operator is the same as the R matrix. So what about other cases?
Well, let's see. So L operators, I mean, coming too. But for example, this rapidity, the fact that R matrix depends on the difference of spectral parameter. Sometimes people call it the rapidity indifference property. That I'm going to assume. Mm-hmm. And that will come, well, the explanation will come later, but basically because this Z will become some coordinate in some internal manifold. And there is some translational symmetry. Mm-hmm. So, which means that everything depends only on the difference. So that's the type of the explanation which will come eventually. But at this point, it's assumption. And also towards the very end, I'm going to discuss a little bit of this R-L relation and see how to see that in this frame, in the framework I'm coming to. Yes, thank you. Indeed, thank you for the question. And indeed, please do ask questions because otherwise I might go too fast. Also, if you cannot hear what I say, please do ask again. Well, let's see. So this is the type of the models which I'm going to discuss. Well, of course, the representation associated with each of these lines can be different. Representation 1, representation 2, etc. But that's the structure I'm going to discuss. And people try to discuss that, for example, taking some symmetry group G, and for each of these lines, I associate some representation of the symmetry group. And this R matrix is, of course, the intertwiner of tensor product representation, etc., etc. So that's the thing people do. And well, that's a very systematic way. Except that, for example, then the starting point is algebra. And if you want to see this integral model, you need to some infinite dimensional algebra, like a Yangian or quantum affine algebra, and things like that. And to some extent, we like to understand even that algebra itself. So we want to start really from scratch rather than starting with the algebra and declare that we're going to do the representation set. And the question is whether there is a way to do that with the help from from quantum field theory. Now, so some of the basic ideas has been around, of course, since the 90s or so, ever since people started working on the 3D Chern-Simons theory. So that was the idea of using the topological invariance. So namely, suppose that these are lines are, suppose that there is some sort of a topological invariance. So these are lines you can regard as a trajectory of a particle, for example. And suppose that on this plane, which is two-dimensional plane, and then you can move these lines around so that because the theory is topological. So for example, if there are two lines, there are distances between different intersection points, etc., like this point and that point. I hope you can see the pointer a little bit. Anyway, so you might, if there is a topological invariance, you might be tempted to say that you can move these lines around so that you can start from the picture on the left and arrive at the picture on the right. So that's the basic idea. So we have a topological theory and we have a particle trajectory or something like that. So that then that might explain conceptually this equality between left and right figures. However, there is a problem if we just naively take that, because when we try to move this line around, there is going to be a singular point when all the lines intersect. And that's the different. Even if there is a topological invariance, this is a singular point, so it changes kind of the topology. It's not isotopy invariant. So the topological invariance in itself doesn't quite guarantee the existence of left and right figures. So you can move this around, move this line around, but you cannot. This line cannot cross the other intersection point. So that's the huge problem in this scenario. Now, if you know the knot theory, etc., people know how to move these lines around. For example, you add one extra direction. And then instead of this crossing, there is a choice of overcrossing or undercrossing. So that's like which line is above or below the other line. And so that's the projection of the knot. And then you can move these lines around indeed, because these three lines don't cross with each other. And then you can, this equality between left-hand side and right-hand side is simply this Rademacher-3 move in the knot theory literature. And that's what it's how Witten explained the knot theory from the three-dimensional topological theory, which is the Chern-Simons theory. Now, so that is very successful, except that he couldn't identify the integrable models. So integrable models, in my definition, it was necessary to incorporate the spectral parameter, which is some complex parameter. But if we just look at the Chern-Simons theory, like SUK with SUN gauge group is level K, etc., there is no such continuous parameter. Simply, there isn't simply any parameter. Well, so there was no hope of explaining the general spectral parameter. But to some extent, spectral parameter is the crucial ingredient because you expand the transfer methods with respect to these parameters, you have an infinite set of commutative charges, for example. So that's an extremely important ingredient, and we have to incorporate that. And the idea is actually very simple. This goes back to Costello's idea, but I'm going to explain it in a slightly more general way. Oh, there is a noise. I hope it's not going to be persist. Okay, so the idea is to go into one dimensions higher. So we have the 4 dimensions, and first of all, there is this two-dimensional plane. This is the original two-dimensional plane where the integrable models live. And suppose, as before, that there is a topological invariance so that you can move these lines around. Now, in addition to that, there is a transverse direction, which is completely independent from this integrable lattice models. And suppose that there is that's two-dimensional, so it's a curve. So I denoted that as a curve C. Now, each of these lines, which is a line in this R2 direction, which is topological, is now also occupies a point in this holomorphic curve. So this line 1, for example, is located at a particular point, so which I called Z1 on this curve, and similarly. And this data is exactly the spectral parameter. So namely, the spectral parameter was always associated with each of these lines. And in the usual discussion of integral models, it's just some abstract coordinate in some curve. But now it's realized rather geometrically as the transverse direction. Now, once you have this setup, then you can indeed move these lines around. Because if you try to move these lines around, again on this R2, it looks like the three lines intersect, and it looks very singular. However, all these three lines are located at different points on the spectral curve C. So, despite the fact that they look like they're on top of each other, R2, but if you look at the whole 4 dimensions, they are never on top of each other. So that means that you can, without any problem, move these lines around and arrive at the other picture. So if you have such a setup, you can automatically solve the Yang-Baxter equation. And not only that, since there is a curve, we also have incorporated the spectral parameter. So this is a very general idea, and in fact, this will work. In fact, for as long as this setup is true, irrespective of which particular 4-dimensional theory you're talking about, etc. In principle. Now, note that that we don't have the full diffeomorphism symmetry in the 4 dimensions. So obviously, the 2-dimensional directions around which the theory is topological is treated very differently from the other 2 dimensions where the theory is holomorphic. So there is a huge difference between the two. And so that's a huge difference from the 3D Chern-Simons theory. So in the case of 3D Chern-Simons theory, you add one direction, but you have the whole 3D topological invariance. But here in this case, the theory is not completely topological. It's partially topological and partially holomorphic. And it looks very different along the which 2 directions you're talking about. And well, if you're familiar with the Lorentz 4D Lorentz theory, with the 4D Lorentz theory, etc., Lorentz invariance theory, etc., in textbooks it looks bizarre. But if you just want to explain the integral models, there is no problem breaking the 4-dimensional covariance. So this is the setup I'm going to discuss. Now, what is the, well, I haven't specified which 4-dimensional theory I'm going to discuss. And of course, that's your choice. And it's interesting to see what kind of possibilities there are. But at least the one concrete theory which Kevin Costello wrote down in 2013 is this Lagrangian. So let me try to explain one by one. But first of all, this A is the gauge field, of course. And this A which the A plus cubic term in A. So this is a lot of standard Chern-Simons term. So Chern-Simons 3 form. Now, okay, so in addition to this Chern-Simons 3 form, we have this extra 1 form, dz, where z is the coordinate on the holomorphic plane. So this c is a spectral curve, and its coordinate is a spectral parameter. So I chose the local coordinate, which is holomorphic, z and z bar, and I just wrote dz, which are the 3 form. So this is a 1 form, and this is a 3 form. So the total thing is a 4 form. And hence you can integrate over the 4 manifold, which is, as I described before, is a product manifold. So I chose the coordinate tx and zz bar. So this is a simple Lagrangian. And in front of everything, I have this 1 over h bar, which is this loop expansion parameter, like a Planck constant. Now, what's a little bit funny is that because of this dz term, this h bar has dimensional length, in fact. So if you know a little bit of quantum field theory, it's a sort of a dangerous theory. So you might worry about renormalizability, etc. But what Kevin Costello did essentially in his paper, at least one of the things he did, is to show that the theory is perturbatively well defined. Okay, so this is the Lagrangian. And well, so what is this? A was the gauge field. So gauge field in 4 dimensions, R2 times C. So it should have 4 components. The TDX, DZ bar, DZ. However, because of this, there is a wedge term, DZ wedge term. The Z component doesn't play any role. So basically, you can forget about it. In other words, there is in addition to usual gauge symmetry, there is extra gauge symmetry shifting the DZ component to the 4 connection. So for this reason, you can essentially look at the 3-component connection. But each component depends on the 4 coordinates. So that's a little bit the tricky part. Now, if you worry about the gauge transformation, you can do the gauge transformation. And of course, if you do the general gauge transformation, you generate this AZ. But you don't care about the value of this AZ. So that's what you're going to do. So that's a peculiar theory, but nevertheless, it's well defined. And this theory is actually, in a sense, the TDO to original 3D Chern-Simons theory. If I have time, I'll come back to this point. And this point might have some relevance to fractional quantum Hall, for example. Let's see. So, okay, then what we're going to do with this theory? Well, this theory is a little bit dangerous because, for example, there's a DZ term, so you have complexified things. So it's not even clear how to define the theory when you do the path integral. You have to take a convergent integration contour, etc. But at least as long as you do the perturbation theory, it's safe. You know how to do the perturbation theory by standard Feynman diagram techniques. And perturbation expands around where? Well, perturbative expansion around the solutions or to the classical equation of motion. And there could be many different solutions, but here I'm going to expand around one of the simplest solutions you can think of, namely the gauge field is completely 0. For example, when the spectral curve is a complex plane. Well, when the spectral curve is a torus, for example, you can consider more general classical solutions and try to expand, and that corresponds to some richness in the elliptic integral models. But let me not try to explain everything, and then try to explain the simplest setup where the spectral curve is a complex plane and expand around the trivial gauge connection. Now, okay, so and then we come back to now that we explained the theory, and then we can come back to the story of having these lines. So this was the original picture, which I was explaining. So namely 4 dimensions and 2 dimensions cross 2 dimensions. Now the line I was drawing now is now a Wilson line of the theory. So Wilson line is a first order exponential of the gauge, so basically exponential of the gauge field. And again, this line is located at a particular point in the spectral curve, which I denote as Z. So the Wilson line depends on this parameter Z, which is a spectral parameter. Note that this is actually the only direction. So this is X direction and T direction. So there are 2 different directions around here. But it's actually impossible to put the Wilson line on this spectral curve because there is no Z component gauge field. And so you cannot do the parallel transportation around here because there was no Z component here. And of course, Z bar and Z are complex conjugates. So if there is no Z component, you cannot move in the Z or Z bar direction either. So in fact, this or the other direction, like a transfer, orthogonal direction. So these are the only 2 possibilities you can think about. And so this is the Wilson line. And then you can go to more complicated stuff. For example, you can make a statistical lattice from a set of Wilson lines. So here I make a statistical lattice where the integral models is defined, and here I place the horizontal Wilson lines to be all located at a particular point Z1, and this vertical Wilson lines to be all located at a particular point Z2 in this vector curve. And so this is the situation. Well, of course, you can make it more general by changing the spectral parameter for different horizontal or vertical Wilson line, for example. But I just show the simplest case where there is a translation symmetry, and this is the type of the picture. So now once you have this picture, you can do various computations. For example, what is the R matrix? So the R matrix, of course, as you know, is associated with the crossing of these lines, crossing of the 2 lines. And there is going to be perturbative corrections. For example, there are 2 Wilson lines, and then you can exchange the gluons in the tree level diagram and the loop diagram, etc. And you can do the perturbation theory order by order in H bar. And that we identify as the R matrix. And what we have done in the part 1 of paper, at least one of the things, one of the small things we did is to do this G-level computation to this Wilson line, crossing of the Wilson lines, and showed that it agreed with the first H-bar correction to the non-R matrix. And then we can of course go to higher orders, and we have some other arguments why computing the first order corrections is enough to determine the R matrix. So we can reproduce the R matrix. So that's the one thing we can do. In fact, in this, what's interesting is that it's a priori unclear whether all contributions localize at a particular crossing. So there might be, for example, Wilson, there might be gluons emitted here, and then travels here, and then emits here, etc. So there can be more complicated diagrams. However, I forgot to say that the series is actually IR-free. So such effects are negligible, don't play any roles. So that's related to this funny feature that this H bar. So I said previously this H bar has a dimensional length, which is, but that means that when the series is free in the long distance. And the theory is topological. Well, I forgot to say that also that the theory is topological because I only used the complex structure of the curve C, and I didn't use any metric on the R2 direction. So on this R2 direction, theory is indeed topological. So you can scale up the metric, for example, and as long as they are not localized at a particular crossing, you can scale up everything. And since the theory is IR free, those effects go away. And that's the logic where things are localized to contributions from crossing, which is this R matrix. Right, so that's a neat computation. And in the final diagrams, if you are interested in the details, please have a look at the paper. So by this type of computation, you can reproduce the R matrix. Now, you can also try to reproduce the Yangian algebra itself. Well, perhaps I should prepare a picture, but for example, the Yangian algebra, so if you want to see the algebra, how to see the algebra. So R matrix is some quantity. But if you want to see the algebra, you can see, for example, this Wilson line and that Wilson line. So they run to parallel with each other. And if you have two parallel Wilson lines, there is something known as the operator product expansion of the Wilson line. So namely, you can take two parallel Wilson lines and then bring them closer together. And then they will merge into a single Wilson line. And that's known as operator product expansion. And if you compute the quantum corrections to that, and then you can see some of the relations of, in fact, what is known as the coproduct of the quantum group, for example, of the Yangian. So that is the type of the computations you can do. R metrics or the Yangian relations, relations with Yangian, and things like that. So that's what you can explain from this framework. Now, so I can explain that continue explaining that, but let me try to explain also the other part of the story. So namely the story of integrable field series. So that's parts 3 and 4. Now, there is one basic idea, which is, of course, that if you start with the discrete lattice model, so this is the setup which I was originally talking about, where this discrete statistical lattice is made from Wilson lines. Now, I can think about the thermodynamic limit, which is, of course, very natural, and then try to see what happens. And we might expect that if you take the thermodynamic limit, this integrable, discrete integrable lattice model might flow to integrable quantum field theory in 2 dimensions in the limit. Well, of course, such a limiting procedure is very complicated. And in many cases, I don't necessarily know how to implement that. There are some interesting papers about light phone limit, etc. But before coming to the details, in fact, we kind of circumnavigate that. But first, let me try to get a good intuition of what will happen. So we're going to take the thermodynamic limit. And then that means that, recall that these lines are Wilson lines. And so if you have the Wilson lines and then take the limit, then the Wilson line will fill in this whole 2-dimensional surface, which I denoted this gray area. So it's a gray area because there are some other defect inside. And in high energy theory, we call these defects surface defects. So originally it was these lines, so it was fitting 1 dimensions out of the whole 4 dimensions. But after the limit, they combine it to fill the whole 2 dimensions. So it occupies the 2 dimensions out of 4, which is codimension 2. So these are called the surface defects. Well, it seems that sometimes surface defects cause line defects in some other like more condensed matter literature, because if you take away the time, it might look like 1 dimensional inside special 3 dimensions. If you take the time to be in one of these directions. But in any case, let's discuss the whole setup, and then if it's 4 dimensions, then these are surface defects. And these surface defects, before taking the limit, so these Wilson lines, horizontal and vertical, are located at a particular point on the spectral curve, which are denoted Z1 and Z2. So, we have a surface defect located at these 2 points, and what we obtain is a coupled 2D system. So originally we have a 4-dimensional system, but of course we have included the surface defect, which is 2-dimensional. So the 2-dimensional series lives inside as a defect, and there is a coupling between 4D and 2D. So they talk with each other. And of course, well, there are 2 different types of defects. That is because, well, located at different points on the spectral curve, Z1, Z2. That's because they are horizontal and vertical ones. So what you have is a system with 2 different types of, together with the original 4-dimensional theory. Now, so let's try to understand the difference between these 2, in fact. And always it's useful to go back to before taking the thermodynamic limit. So what is the difference between horizontal and vertical defect? Well, of course, they spread in different directions. So, but in practice, what that means is that they couple to different components of the gauge field. So, so recall that these lines are Wilson lines. So it's just the integral of the gauge field along some component. And let's take this horizontal direction to be W direction, and vertical direction is W bar direction, where these W and W bars are light phone coordinates. So T is time and X is a spatial direction. Tx is the coordinate on this R2, and I have taken this light phone direction. And that means that the 2D surface defect couples to different components of the gauge field, AW bar and AW, and that's the difference between the 2. So if you take the limit, that means that there are 2 surfaces different because they are either chiral or anti-chiral. So there is a coupling between this, one of them, say this one, couples to AW bar component because there is a current, 2D current, which has only W component. And that is known as a chiral theory. And vice versa, there is also anti-chiral theory. So what we learn is that we have a couple for the 2D system, and one of the defects is chiral, and another defect is anti-chiral. And we expect that the prediction from the thermodynamic limit is that this thing should be integrable. So how do you see that? Well, of course, previously we had the Yang-Baxter equation arises from the topological invariance on the plane, but it's not obvious what it happened to that in the process of thermodynamic limit. And understanding that is a question why that such a coupled 4D system is integrable. And then you can go back to the standard discussion of classical integrability in 2-dimensional field series. And that's the presence of the Lux operator. So that's a different criteria from what I was talking about before, but that's the existence of the Lux operator. And it's actually very easy to see the existence of Lux operator in this framework of coupled 4D system. But so we have a gauge field in 4 dimensions, and it has component W and W bar. So I just defined the form L of Z as this thing. So this AW, etc., it depends on the coordinate in the extra direction. So it depends on all the 4 coordinates. So in particular, it depends on this Z, holomorphic coordinate. So this LZ is not, that LZ is now regarded as one form in 2 dimensions in this R2 direction. And then you can compute this flat connection condition, so the field strengths for this Lux operator, and you can easily compute this. So this is a one form, and with coordinates on R2 with coordinates given by W and W bar. Oh, sorry, there is a bar W bar here. And then of course you easily find that it's proportional to W bar component of field strength. However, that's 0 because of the equation of motion. So recall that the Chern-Simons term is A with F essentially. So if you vary with respect to A, all the components of F is 0. So this is the 4-dimensional equation of motion. So this is the explanation that that if you impose the 4-dimensional equation of motion of the 4-dimensional bulk gauge field, and you automatically have this Lux operator satisfying the flat connection equation. And people discussing integrable field series are excited about this because you can construct infinite many conserved charges from this by taking the first order exponential of this L Lux operator, and everything is a function of Z, this holomorphic coordinate spectral parameter. So you can expand to obtain this conserved the charges, which I denote Qn, where n runs from 0 to infinity, 1 to infinity. And the flatness conditions ensures that this W of Z is independent of time. Which means that when expanded with respect to Z, this Qn, the coefficients are always independent of time, so they are conserved. So this is how you see the classical integrability of this coupled 4D2D system. Now, there's a sort of well, so far, in fact, in most of the integral model literature, this L operator appears, Lux operator somewhat appears as a sort of a gadget and doesn't necessarily have the direct physics meaning in itself. However, in our context, there is a clear physics meaning, namely this expression. So that's W equals the first order exponential L, but this L is simply the gauge field I defined above. So this thing W, so this W of Z, which I was expanding, is simply the first order exponential of the gauge field, which in 4 dimensions is nothing but this 4-dimensional Wilson line. So the Lux operator is not just a gadget in this framework, but it's really the fundamental physics object, the gauge invariant operator in the 4-dimensional theory. So namely the 4-dimensional Wilson line. So the slogan in this context is that the integrability of the 2-dimensional field series exists simply because there are 4-dimensional Wilson lines. Now, so this explains the integrability, at least at the classical level, except that, we have explained the integrability for the coupled 4D2D system. And that's usually not something which people talk about. Well, people talk about ON model and things like that, so it's not a coupled 4D2D system. So if you want to connect to the effective 2D system, well, to the purely 2-dimensional system, then what you should do is to integrate out along this curve C to obtain effective 2-dimensional system. And for that, you need to make sure that there are no zero modes around this curve C. And once you make sure of that, you can just integrate them out. They are like a KK modes, like they are massive, so you can integrate them out. And you can see what effective 2D series we obtain, so that you can compare with the literature. Well, first of all, as I said, we have to make sure that there are no 4D zero modes. And this is not always guaranteed. However, well, of course, if you expand around isolated classical solution of the equation of motion, for example, a gauge equal to 0 for when the spectral curve is a complex curve, like a solution like this, there is no moduli to this classical equation of motion, which means that there is no zero mode when expanded along the curve. So when you do this integrating out this procedure, you first have to identify the zero modes and then see what kind of action it has. But all the zero modes come from 2-dimensional surface defects. But of course, the two-dimensional surface defect in itself can have the zero mode. So that means that the only non-trivial interactions come from the exchange of the four-dimensional gauge bosons, and that's the it mediates the interaction between chiral defects and anti-chiral defects. So this is a schematic diagram. There is a 2D surface defect inside 4 dimensions, and another 2D surface defect, and they exchange the gauge boson, which is represented by wavy line here. And then you can easily do the computation. There is a coupling, so there is a vertex. The current, which I denote by J, couples to the gauge field, and there is a propagator in between. And you can also count the power of H bar and see that it's power of 1 over H bar. So one of the power cancels there is 1 over H bar, and that's the same as the action. So that contributes to the classical effective action. And it turns out that this simple diagram is actually the only diagram contributing at the tree level, at least. So usually, if integrate out is a very complicated procedure, but in this case, it's actually very simple. Well, for example, you might imagine that there might be more complicated diagram like this, where there is one vertex. This is still tree level diagram, but it's a little bit more complicated. However, there is no such diagram because the anti-chiral defects and chiral defect couples to different components, AW or AW bar, and there's a propagator, but it doesn't couple to AZ component. So if you try to write this diagram like this, at the vertex in the middle, there is going to be a vertex of AW and 2 W bars. But in the Chern-Simons theory, the interaction vertex is anti-symmetrized because it's a wedge of the 3-1 forms, and hence this is 0. In any case, we only need to compute this diagram, and it's a simple Feynman diagram computation, except that there's one clever way of doing this computation without actually doing any computation, which is to notice that this thing, the exchange of gauge bosons, before taking the sum dynamic limit comes from this diagram. So these two surface defects, before taking the sum dynamic limit, but just this line, the Wilson line. So if you want to compute this diagram, then, well, you can think about the meaning of this. And this computation represents the first correction to tree-level correction to Wilson lines crossing vertically. And this, as explained, is the first non-trivial correction to the R matrix. So R matrix depends on this expanded parameter H bar. And the first leading piece is 0, identity, trivial. But then there are also quantum corrections. So that's known as the classical R matrix. So I here have the R matrix, which is quasi-classical, has the H bar expansion. So that means that this diagram, which I wanted to compute, is actually this a classical R matrix. Now you can come back to the effective theory. So in the effective theory, we have first the whatever degrees of freedom at the chiral defect and anti-chiral defect. And originally they are completely, they don't talk with each other, they're independent. But then there is a coupling through the current. So JA and JB with W and W are components because they are chiral and anti-chiral. And you contract the indices with this classical R matrix, RAB. So this is the Lagrangian. And once you have the Lagrangian, you can try to compare with the literature and see what we obtain. Well, not just the Lagrangian, you can also try to do similar things with the Lux matrix itself, because that ensures the integrability, and that's something you might want to compare with. So for that computation for that is similar. So the Lux operator is basically the gauge field, AW or AW bar. And if you want to compute that in the effective theory, you write a similar diagram, except that now with the insertion of AW and AW bar. So for example, there is AW here, and that contributes this effective vertex here, and you compute the propagator inside. So that's going to be this effective Lux matrix. So that's a very concrete expression. And now you can compare with the formula known in the literature. And for example, in the simplest case. So let's consider the rational case. Rational case means that the spectral curve is simply the complex plane. And the classical I matrix is given by this formula, where it's Casimir divided by Z. Well, you can reproduce this from final diagram computation if you like, but it's also a well-known formula. And we can plug in this the expression of the classical R matrix to here and there, and the Lux matrix, Lux operator takes this form where J is a current, so it's a combination of W and W bar component of current, and it has poles at 1 and -1, and they correspond to the location of the surface defect, which I chose to be 1 and -1 in this example. I can choose other values, but to compare with the literature, I have taken these values. So this expression of the Lux operator now has a more physical meaning, that there is a divergence because of the presence of the surface defect, for example. And I explained this here in the case of the rational case, the simplest case, but of course the logic generalizes to other cases. So let me briefly comment on some generalization and examples. So, well, one of the simplest cases of defects are like a chiral or anti-chiral fermions. So anti-chiral chiral fermions feature denote psi, and anti-chiral fermions feature denote psi bar. And then there is so this is a free fermion, and the free fermion is a 2D defect which couples to 4D. So suppose that this has some free fermions have transform under some global symmetry, and you can gauge that global symmetry and couple to the 4D system. And then there is a current, which is basically psi or psi bar. And this was what I was the J and J bar before. And there is a coupling as coming from the classical R matrix. So this is a very simple expression. And depending on which representation you're talking about, you can compare with the Gros-Neubeu or Tilling model, for example.
Excuse me. May I ask a question? So where do fermions coming from? So far there were no fermions, so could you please elaborate?
Oh, that's right. So the fermions come from the surface defect. So here, for example, right. So in the discussion, well, sorry, let's see. Maybe there is a more effective way to move this around. So here, maybe here. For example, in this setup, we have first of all, we have the 4-dimensional theory, which fills the whole thing. But now we have the surface defect, which fills this R2 and a point. So the surface defect means it's just a 2-dimensional Lagrangian. And here I haven't specified what kind of a surface defect it is, but I can imagine that there is a free fermion which lives on this R2 and located at a particular point in this spectral curve. And in fact, you can take the construction is very general. You can take any theory. In fact, it doesn't even have to be chiral or anti-chiral as I come into. But say let's take some chiral 2-dimensional theory, free or non-free or interacting, etc., with the global symmetry G. And then you can gauge that global symmetry to couple it to 4D theory. Sorry, is that clear? Am I answering your question?
So your starting point, any chiral theory in 2 dimensions?
Yes, that's right.
And then you can make integrable theory out of it.
Exactly, right. So yeah, in fact, you can make, in this case, I can take any one chiral theory and another anti-chiral theory. And let's say with the Lagrangian. I mean, well, probably we can talk about non-Lagrangian theory, but say suppose it's a concrete Lagrangian. And then I can reproduce the integral model classically at least.
Okay.
Yes, so that's a statement. And in fact, in some cases...
So just a question, sorry, about this fermion. So you do not have to choose this fermion such that it absorbs the anomaly of the theory? Because now you have the boundary?
Of course. Yeah, that's right.
So it's not any chiral theory, it's something that has the correct anomaly, right?
Oh, yeah, of course, that's right. So as far as the classical integrability, first of all, as far as the classical integrability is concerned, I think this construction works. Now, there might be quantum corrections and anomalies, and you have to make sure that the anomalies are cancelled. And that will ensure quantum integrability, which I'm coming to afterwards. So, in order to make sure of that, well, first of all, chiral defect definitely, as I said, contributes anomaly, localized at this particular point in Z1. And also, this anti-chiral defect contributes anomaly, like a Z2, localized Z2. And the trick is to absorb these anomalies coming from the chiral anti-chiral defect by modifying the Chern-Simons term. So that's like an anomaly, well, what high energy physics called anomaly inflow. So namely, there is a cancellation between 4D anomaly and 2D anomaly. And that puts some constraint on some matter content. For example, I forgot the formula, but maybe something like a deep quadratic Casimir, the summation of the quadratic Casimir. Well, in this case, if it's just a one chiral defect and one anti-chiral defect, the quadratic Casimir for chiral and anti-chiral should be the same, etc. So there is some constraint where such a cancellation can happen. Okay. So we can talk about various different examples, but the simplest case is free fermion, which is already somewhat surprising interesting. Well, for example, you can also, even in this example, you can change the spectral curve to be C star or elliptic curve, and you can discuss rational trigonometric or elliptic cases very systematically. And this, in that case, so in the rational case, this is 1 over z. In general, this is going to be the Green's function on the corresponding curve, like a theta function and things like that. And so you can discuss, even in this free frame example, you can change various representation, various groups, and also elliptic, rational, trigonometric, etc. And if you're skeptical, of course, you can always check directly at this level the flat connection condition for the Lux operator. Now, you can also try to do more general defects. For example, there is something known as the curved beta gamma system. So this beta and gamma, so this gamma is a map from the map onto some manifold, which might be curved. So that's why the name curved beta gamma system. And it couples through the covariant derivative A, which is the bar gauge field. And well, if you're interested, I could explain in detail later. But there is a way to obtain the sigma models with a target. For example, like a poset G over H, homogeneous space, etc., from this beta gamma system. Well, of course, these are free fermions and beta gamma systems. They are very special examples of the defects, but they're already powerful enough to construct various different examples. And also, you can also have multiple defects. Okay, so now let me explain. Well, okay, time is running, so let me try to explain quantum integrability somewhat quickly. And of course, there was already a question that about how to see the quantum integrability. I know there might be anomalies, etc. Well, first of all, you have to make sure that the whole setup is consistent, and that question is tied with the question of quantum integrability. So, for example, CPN model where n is greater than 2, greater or equal to 2, is known to be classical integrable, but not quantum integrable. And so you have to make sure that the anomaly is cancelled, which you can do by modifying Chern-Simons levels. But let's for the moment, let's discuss that works. That puts some conditions on what type of defects you can include. But let's suppose that the anomaly is cancelled. And then how do you see the quantum integrability? So the logic is like this. But first of all, recall that in the classical integrability, in that discussion, the Lux operator came from the 4-dimensional Wilson line in the coupled 4D, 2D frame. And in that discussion, we have to close the Wilson. So it's a Wilson line. So it actually has to be a closed curve. And in the typical definition of integral discussion of integral models, you compactify one of the directions, the special directions on the R2 to define this object. However, you can also consider R2. So sort of decompactify this S1 direction and consider the Wilson line, which I denoted gamma. And then, well, now this is not a closed curve, but nevertheless, it's still an interesting object. And what I denote T of Z, so that's this first order exponential, that's the Wilson line, can now be regarded as an operator from the state, in state, at infinity to another out state at infinity. So there is an X direction, so this is a special direction, which is now decompactified. And now I'm implicitly assuming that the theory is massive. So, so this operator can be sort of a map from the in state to the out state along this special direction. Now, I'm incorporating this Wilson line operator at the position Z, and those Z's are different from the Z1, Z2, which are the locational surface defects. So we now have 3 special points. And now we can consider 2 Wilson lines. And well, the theory is still topological along this R2 direction. So we can move these lines around, and then there's 2 intersections there. And of course the theory is topological, so you can put out these intersections to infinity, which I might schematically like this, where there are 2 crossing at infinity, and otherwise they run parallel. And this gives the RTT relation. So we have the product of R2 tensor, the operator, which is denoted T. So these are the Wilson line, but now these are regarded as operators. And here I have the same set of operators, but the different ordering, but they're the same up to this crossing, which is the R matrix. So this is the definition of the Yangian. So so this statement, which almost trivially follows from topological invariance along the R2 directions, ensures that the theory is quantum integrable. So that is what we discussed in part 4. And in fact, we did a similar discussion for integrable lattice models. So this is, the discussion here is for integrable field series, but we also discussed RTT relation for integrable lattice model. So in this case, there are no surface defects, but rather we have 3 Wilson lines. And again, using the topological invariance around this direction, we can change the left-hand side to the right-hand side. Now, the point is that this T, for example, so this Wilson line is now regarded as an operator acting on the state on another Wilson line crossing orthogonally. And that's the spirit of this RTT. So you can reproduce this RT relation for also for discrete lattice models. And this is one of the ways to see the Yangian relation to all orders in perturbation theory. Because some of the explanation I provided before uses the Feynman diagrams, so it's easy to do some first few orders in computation, but it's not easy to see the all order part structure. So we have to rely on some general theorems, etc. But using the RT relation is one way to see that. And in fact, the argument is general, and also we also have the vertices. In fact, so interesting, we have a complete RTT presentation for a lot of groups, like for example G2 or E8, etc. You might know that in the RTT for SLN involves a quantum determinant, but we now have a counterpart of quantum determinant for a variety of group algebras like E8, F4, etc., which seems to be actually new. But that's something you can easily find from, but not too easily, but easily find from quantum field theory viewpoint. And our 4D framework says many more, including not just the non-local charges, but also local conserved charges, which are completely separate, but nevertheless sometimes useful to see integrability of the model, RG flow, and S matrix factorization, etc. So all these things we are now working on, fitting some of the details. So please wait for our paper. Now, well, sorry, I'm going a little bit over time, but maybe I could spend 5 minutes, I guess, about because there are some people. I guess some of the people here are interested in not necessarily the mathematical, not just the mathematical physics aspect of that, but maybe something a little bit broader. And I think it's an interesting question whether the type of the 4D Chern-Simons theory I talk about has any relation to this. And the short answer is I don't know. And in fact, I'm completely ignorant about the whole subject. But nevertheless, so what I'm going to say from now might be completely wrong. But nevertheless, it might be interesting to say something. So, well, first of all, let's start with the 4D Chern-Simons term. This is the action. And you can do the standard integration of parts. Oh, sorry, there's no which is not necessary. But here, then you have just a theta angle term. So FH, standard FHF. So this Z is the theta angle. So this funny action which I was talking about means that it's a usual Chern-Simons action with the topological theta angle. The only difference is that the theta angle is holomorphic in one of the two of the directions. Holomorphic. So holomorphic theta angle. So it's just that. And that's usually not allowed because if you impose a time reversal symmetry, etc., theta is 0, pi. But let's assume that we do not impose such a thing. Then, in principle, this might be allowed. And in fact, I don't know how to realize this. So, but there might be a little bit easier version, which is instead of considering this holomorphic coordinate, let's take one of the coordinates. Let's take x, and consider this theta angle, which is linear in x. So this is not holomorphic, which is actually important for many purposes. And in fact, if you want to define perturbation theory, there is some problem with this because, which I wrote I wrote something here. But anyway, nevertheless, you can try to think about this theta angle, which is linear in one of the directions. Now, what is the implication of this? Well, I don't really know, but at least you can try to compute the current by taking the derivative. And if you take this derivative, so there is this dx with Chern-Simons term, and you can take the derivative, and the current is basically proportional to f. Well, if one of these directions time coordinate, it's just the electric field. And there is epsilon tensor, but electric field, and there is one of h bar which might be quantized. So this ijk's are 3 coordinates. So recall that I have 4 directions, still 3 plus 1 dimensions. So 4 dimensions, which condensed matter people might call 3 dimensions. And then the 4 dimensions, out of 4 dimensions, I chose one particular coordinate. And the remaining coordinates I denote the ijk, which are supposed to be anti-symmetrized. So we find something interesting, which is very similar to the more standard fraction of quantum Hall, but up in 1 dimension. So, and it seems that as far as I see, I could try to understand from some of the Greg Moore's paper these days. This seems to be essentially this 3D quantum Hall effect, as discussed by Fabian long ago. Well, in fact, if you know anything about the subject, I'd love to learn, but that seems to be the case. And usually, well, 3D quantum Hall is considered to be a little bit boring because it's like a 2D quantum Hall, and there is a layer of that stuck together. And in my way of Chern-Simons language, it just means wedge by dx. So people say that, well, 3D quantum Hall, well, I don't know who says what, but in some of the literature I read, people are not too excited about 3D quantum Hall because it's just a layer of 2D quantum Hall. In fact, some of the formulas look like that. However, the 4D Chern-Simons theory I was talking about with this holomorphic coordinate ZZ is actually very interesting because it explains the integral models, and there's all these structures. And if you do the T-duality, so this 4-dimensional Chern-Simons, 3D Chern-Simons are related by T-duality to some extent. And if you do the T-duality correctly in field series and string theory, you obtain this holomorphic coordinate. So, so it might be the case that by stacking the 2-dimensional fractal quantum Hall, but not in the real way, but in the holomorphic way. So we might realize this 4-dimensional Chern-Simons theory, which I was talking about, and hence some interesting version of 3D fractional quantum Hall. And if somehow this might work, it might be that particles should be the representation of Yangian, so Yangian statistics or something like that, or maybe to some extent, maybe in a sense, we are realizing integral models in the lab. These are just a little vague thoughts, and but if you have anything interesting, please let me know. So I'm running out of time, so let me try to summarize. So in the discussion I had, I start with the 4-dimensional perspective. I always start with the 4-dimensional perspective. and the 4-dimensional Chern-Simons theory here with the 1D defect, namely Wilson line included. And in other parts of the story, we have the surface defect included, the 2-dimensional defect inside 4 dimensions. And in each of these cases, you can forget about this, well, you can pretend that, forget about this curve, spectral curve, and then you obtain a more standard construction, namely integrable lattice models, or in this case, integrable field series. But the 4D perspective is very powerful. It geometrizes the spectral parameter, and hence explains why it's a spectral. There are spectral parameters why the series is integrable, and also it's also useful for computations, and it gives rise to many new integrable models. Okay, so I seem to be out of time, so let me finish here.
Thank you. Let us thank the speaker. Any questions? I have very general questions. So this is new formalism, gives some geometric picture of integrability. So what is it? What is it good for? What kind of problems you think will be easier to attack with these formalisms than with standard ones?
Oh yeah, that's well. Of course, that's well. First of all, well, right. The very first motivation for me is to come up with a framework where the integrability itself is made manifest. So, namely, well, rather than using integrability as an input, I want to have a theory where integrability is automatic. So that's a conceptual point, which I hope I conveyed. But now, more practical level, like can we do anything new, etc., with this? And in that respect, the integrable field theory example, which I talked about in the latter half, seems to be very powerful. So, namely, as you pointed out, you can include the various defects and various surface, chiral, anti-chiral, etc., and it automatically guarantees classical integrability. And so it seems to give rise to a lot of new integral models, first of all. And besides, we can also, well, I didn't have to talk about that. You can talk about RG flow, etc. Points move around. And so that's, discussion of integral field theory seems to be one point. But also the whole setup is actually embeddable into string theory, for example. And then you can try to do various string dualities, etc., to relate this integral model to another integral model in a analyzed in a different way. And that will hopefully give rise to new relations in integral models among themselves. But for example, you might have heard that Nekrasov and Chattoshvili has been working on their version of the story, trying to connect integral models to some field series. And but this is a rather different approach. And I think people are now developing the story, try to connect the story. And through this chain of string dualities that will produce some concrete statements relating one to the other. And there are some hints, for example, some of the ingredients might be already known in the literature. For example, there is a work by Bajanov and Stroganov about connecting chiral pots to XXZ, and that seems to play some important role in the whole story, for example.
Okay, thank you. Other questions? Okay, if there are no more questions, let us thank our Masahito again. Thank you.